Hey folks, welcome back. In this video we're going to go over 3 worked examples to show you how to do problems involving doping. Now if you haven't already done so, check out my previous videos covering the theory on doping, N-type doping and P-type doping, as watching these videos will help you understand what we do here. So let's get started. Question 1a first of all asks, why are semiconductors doped with impurity atoms? Well, remember the whole point of doping in general is to increase the conductivity of the semiconductor, or in other words, to decrease its resistance. Part B says, what are the majority charge carriers in N-type semiconductors? Well, remember, in N-type semiconductors, the majority charge carriers are the negatively charged particles, which are electrons. And remember, you can think of N for negatively charged to help you remember this. For part C, it says, what are the majority charge carriers in P-type semiconductors? So remember, the majority charge carriers in P-type semiconductors are holes. So you could think of the P for positively charged to help you remember that one. However, a key thing to remember is that both N-type and P-type semiconductor materials are neutral overall, even though they have different majority charge carriers. Question 2a says to explain with the aid of a diagram how silicon can be doped with arsenic to become an N-type semiconductor. Well, firstly, remember that arsenic is a group 5 element, meaning it has 5 outer electrons available for bonding. Silicon, on the other hand, is a group 4 element, meaning it has 4 outer electrons available for bonding. When silicon is doped with arsenic, its 4 outer electrons bond covalently with 4 of the arsenic electrons. This leaves 1 electron free to move about and conduct. And here's a diagram you might draw in order to support the answer. So you've got these silicon nuclei here surrounded by electrons. We've then got the arsenic nucleus in the middle here, which is bonded to all the neighbouring silicon nuclei through the electron bonding. And you can see we've got 4 of the outer electrons for arsenic bonding with 4 of the outer electrons for the silicon nuclei that are surrounding it. And then we've got this extra electron here. Part B says, what effect does N-type doping have on the resistance of a semiconductor? Well, we can say that since the ability of the crystal to conduct is increased by the movement of free electrons, the resistance of the semiconductor is reduced or decreased. Lastly, question 3a says to explain with the aid of a diagram how silicon can be doped with boron to become a P-type semiconductor. So this time we're looking at P-type doping. And firstly, we can say that boron is a group 3 element, meaning it has 3 outer electrons available for bonding. And just like in question 2, silicon is a group 4 element, meaning it has 4 outer electrons available for bonding. So this means that when silicon is doped with boron, 3 of its electrons bond covalently with the 3 boron electrons. This creates a hole in the crystal lattice where an electron is missing. So remember, a hole is just an absence of an electron, but we can think about it as being its own positively charged particle. We then say that an electron from the next atom can then move into this hole, meaning conduction takes place by the movement of positive holes. And if you were to sketch a diagram to aid your answer, it might look something like this, where we've got our silicon nuclei with 4 outer electrons, and we've then got a boron nucleus in the middle with 3 outer electrons that are bonded covalently to neighbouring silicon electrons. And you can see we've got this missing electron here, which means we have a hole in that position. Lastly, part B says, what effect does P-type doping have on the resistance of a semiconductor? Well, it's just the exact same effect that N-type doping has on the resistance of a semiconductor, but it's just carried out in a different way, as we've seen. So just like we said in question 2, since the ability of the crystal to conduct is increased by the movement of positive holes, or in other words, conductivity increases, then the resistance of the semiconductor is reduced or decreases. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.